And, well, people at Forntal Institute try to develop mathematics that fit this idea of mathematics as an activity. And looking at what the things people have done, Travers generalized over all this work and developed a theory for holistic mathematical education. And later, he translated it into 3 design heuristics. Guided reinvention, already mentioned by Forntal. Didactical phenomenology, also mentioned by Forntal. And emergent modeling. And I will just go through these principles quickly. In guided reinvention, you start with identifying the starting points that are experiential and real for the students. And you identify where you want to go. And then you look at the history of mathematics to look at potential barriers or dead ends or breakthroughs. That gives you ideas how students could invent much faster than history showed you. You could also look at informal solution procedures because they might sort of anticipate more formal approaches. And I will use addition and subtraction to 20 as an example to work out. So guided reinvention there means you start with informal solution procedures in context. And there are a lot of strategies students use spontaneously, like doubles, 5 reference numbers like 8 is 5 and 3, 10 reference, and that relates mainly to counting on their fingers. But these are things they know or developed over time. And what you want to reach then, building on those knowledge, you want to reach a level of flexible use of number relations. A sort of derived facts, and I'll just show you. So for instance, if they're looking at a task like 7 plus 8, you hope that all kinds of number relations come to mind. They think, oh, 7 and 3 is 10, 8 is 7 plus 1, and so forth. All these things that come up. And then they can make combinations, like knowing that 7 is 5 plus 2, 8 is 5 plus 3, you could combine the 5s and you could go on. What I want to emphasize here is what the students are doing, they are flexibly using the facts they know. They're not following some procedure or strategy. They don't go and see 7 plus 8 and say, what will I do? Will I fill the 10, or will I go for the doubles, or will I look for the 5? No, that's not what they're doing. They use what they know flexibly. And so the basis is in number relations. The didactical phenomenology asks you to analyze how mathematical things, as Forntal calls them, concepts, procedures, or tools, to organize certain phenomena. And then you can think of a task setting where students are forced or pushed to invent those things. And if you go back to addition and subtraction, then you have these phenomena like you have all those kind of situations where you have addition and subtraction, where you combine things, change sets, or compare quantities. And Forntal points out it is not just combining sets of objects, not only the cardinal aspect, it's also measuring, counting on, and so forth. So the trick is to coordinate the cardinal and the ordinal aspect of number. And he observes that most often we have a problem that is stated cardinally. We have 4 marbles and 3 marbles, and then we solve it ordinally by counting on. So these are the things that sort of guide you in designing instruction. The third heuristic is emergent modeling, and that relates to what's called circumventing the learning paradox. And the problem is, from a constructivist view, external representations don't come with their meaning. For people who haven't seen them for the first time, they only see the representations. So Gravemeijr says, how is it possible to learn symbolizations which you need to come to grips with new mathematics, if you have to have mastered these new symbolizations to be able to understand those symbolizations. So the symbols derive their meaning from the mathematics, but to get into the mathematics, you have to understand the symbols. So you sit in a vicious circle. And you can, if you look at history, you can, and this was my idea, you can see how you can circumvent this problem by building up symbolizations and meanings, starting with this very simple, straightforward symbolizations, work with it, developing a new meaning, higher level symbolizations, and so forth. And then you don't have this problem. So modeling then, that is in service of the learning process. So the starting point is in modeling situations that are familiar to the students, and the model derives its meaning from the situation. Later on, the shift is to mathematical relations, and the model starts deriving its meaning from those relations. So it's a model of mathematical activity that becomes a model for more formal mathematical reasoning. And of course, often it is a series of submodels. To go back to addition and subtraction again, you could think of doubles in the 5 and 10, reference things that you're working on first, in context and so forth. And then we have the example of the story of the double-decker bus. And in the double-decker bus, you can sit on the upper deck or on the lower deck. And you can symbolize it briefly with a sort of H, with on the top the number of people on the top and below the people on the lower deck. So you have 15 people, that could be 10 above, 5 beneath, and so forth. And then we introduced the so-called arithmetic rack, which I'll show in a minute, to scaffold and describe this situation. The arithmetic rack is a rack with 20 beats, colored dark and light to emphasize the 5 structure. And what's on the left is the numbers that you're working with. So now in the middle we have 9 on the top and 6 on the bottom. And so you can think of how to add 9. Oh, sorry, 7 on the bottom. Well, it's changing. Never mind. The last one is 9 plus 7. And there are various strategies for solving problems with the arithmetic rack. For instance, you could say, I look at combine the 5s, then I have 10, and then another, in this case, 5. Or I could think of 7 and 7, and look at those beats and see what I have extra. What's an additional thing here is that in an experiment we did in Nashville, it's called Jekyll and Whiteneck, is that we introduced the symbolization of this representation. So there's a new symbol which gets you closer to the mathematics and further from the context. The idea is that when students are working with this rack, they are thinking about number relations like 5 plus 2 and 5 plus 3, and that's put on the rack. So they first think of the number relations and then put the numbers on the rack. The idea is not that they're reading off and counting beats. So they have to know already a set of number relations when they start using it for scaffolding their thinking. And then you could say, well, in first instance, the rack was a model of the people on the bus, and it became a model for mathematical reasoning, which you then further formalize. So this about RME, which is sort of, I would say, implemented in the Netherlands. It is in many textbooks, but of course there's a translation from the ideas to the textbooks, let alone what teachers do. The problem in the Netherlands was that we had little room for teacher professionalization. The government didn't see this as an issue. So the curriculum innovation was mainly via textbooks. And we found that RME wasn't enacted as intended. It was already in 1991 that we saw that what teachers did, they tried to do, they followed the intentions, but what they did was something different from what was intended. And then, several years ago, we had these national surveys where you show what students are able to do at the end of primary school. And it showed there was a decline in operations and especially standard algorithms. There was some improvement in number sets and global arithmetic, but people who didn't like the innovation jumped on it and saying, well, there's a decline, especially in the important things, so as the algorithms. And they got the floor both in the media and with government. So we had our own math wars, and now still there's a very strong emphasis, at least on a more strategic level, that everybody should practice, train, and so forth. But it was also a reason to start to investigate what's really happening. And as Dirk already said, in general, the results are not bad. Netherlands is still up high if you compare to other countries. But we may wonder if the high goals we had for realistic mathematics education are reached, and why, if it isn't, why it happened. So three people did a PhD project on this, one on subtraction up to 100, one on multiplication of fractions, and one on algebra. And these were independent studies, so were differently organized. Jean-Marie Gravemeijr looked at subtraction up to 100, and he distinguished different strategies that students could use, such as jumping or counting on in jumps, or splitting tens and ones, or reasoning, trying to derive number facts, or just know some facts you already know. If they ask you what is 75 minus 25, you know the answer without a procedure. And he investigated what students were doing. And what he found is most of the students use some sort of jumping strategy. And that has to do with the number line that was introduced in the textbooks based on the work of Travers. So that's what most students did. And it showed that it was an effective method. They also used it flexibly, only they also did other things, like splitting, which got them many incorrect answers, and reasoning, which also got them many incorrect answers. And that made that the whole total wasn't better than the several years before. The problems they ran into were buggy algorithms, subtracting smaller from larger, or incorrect forms of splitting or reasoning, and bridging 10 appeared difficult. So, in general, we could say they have a, a limited understanding of, they had a limited understanding of inverse relations and a lack of proficiency. Just in general, they had a restricted set of strategies they could use for computing, and they didn't have a conceptual understanding. And then he looked at textbooks, and then you see it starts nicely with context that students understand and build on this, but then progress to a higher level of number relations is not happening. There's little attention for splitting in tens and ones. This whole idea of tens is not very well developed. And we think there was an appeal of procedures that worked, using those numbering strategies that worked for the students, worked for the teachers, worked for the textbook authors. So that's where the emphasis was, having direct results. But students themselves would start doing other things, like splitting. If they have to add 24 and 24, they will say, well, do 20 and 20 and 4 plus 4. However, if they try the same thing with 44 minus 28, they run into problems. Then the fractions. This was studied by Gravemeijr, and she focused on multiplying fractions. And I just have an overview of the results, and in short, you could say they have a lot of problems with fraction, and this is then in early secondary. well, I'll skip the details. If you look at textbooks, then you see that there too is an emphasis on on number-specific solution methods. And there are basically two methods. The one is built on the idea that you have the context of a number of cartons of 3/4 of a liter, and then you do it, have say 16 of them, and then you can use repeat addition. However, you could also have a situation where you have 3/4 of 16, and maybe you write it in a different order. Then you first take 1/4 and you do it 3 times. So there are two different ways of calculating the same multiplication. But students will do it differently because the order is different. And then there are 2 other methods that they use on also using area and things like that. So in matter of fact, the students have 4 different procedures. And so, but the next step, why 16 times 3/4 is 3/4 times 16 is the same, is not answered, is not looked at. And so on the other hand, the students are very much tied to concrete situations and always numbers in context with some measure, liter, gallon. So to understand the rule for multiplication of fractions, you have to think of numbers as objects, using relations. And that's from in secondary school, where they just start with the rule. And they give an example with an area model, and then you know you have to multiply the nominators and the denominators. For the students, this is just a 5th rule. So now they have 5 rules they can choose from, and of course they start mixing them up.